Let's move on to example D here. I think that this would be a good example if you are starting to feel a little bit comfortable with the strategy to just pause the video and try on your own. So if you'd like, we've talked about similar examples up above, so I think that you might already be comfortable enough to try this, but if you are still sort of lost, then we'll start talking through it. So pause the video if you want to try it. So remember that again, we're looking for an inside function and its derivative somewhere. So I see this inside function because it's being raised to the fourth power, and I notice that its derivative is sitting around here on the outside. So on the outside, I have a 2x minus 3, which is the derivative of the inside expression there. So it's probably a good idea to let u equal that inside expression. And then taking the differential on both sides, you would get that the derivative, well, I should just say du, is equal to the derivative on the right side times a dx. And again, if you would like to just divide both sides here by dx so that this looks a little more like what we had previously, then that would be totally fine. But in my opinion, it's a little bit nicer to write it this way all on one line, just so that we can replace that 2x minus 3 dx with a du right away without having to worry about any additional cancellation. So let's rewrite this integral in terms of u now. We know that the first underlined expression can be replaced with just a u. So this would be a u to the fourth power. And then the second factor, this 2x minus 3 times a dx, that can be replaced altogether with a du. So I would end up getting the integral of u to the fourth du. Now I've gotten rid of all of the x terms, so I can just integrate this with respect to u. To integrate a power of u with respect to u, I should just add 1 to the power and then divide by the new power. So this is u to the fifth divided by 5 plus a c, because we just took an antiderivative. And now for my final answer, I'm just going to replace that u with its original expression in terms of x. So I should get all of that stuff to the fifth power divided by 5 plus c. And that's what we're looking for. So next what I want to do is I want to talk about some alternative things that you can do with this differential notation. So we've already seen how to integrate this. This was the same function that we took the antiderivative of in b. The factors are just rearranged a little bit. So in b we had e to the 5x times 5. Here we have a 5e to the 5x. So we're going to get the same thing again, but I just want to start introducing one extra thing that you can do with this differential notation, which can be to your benefit. So here I look for an inside function. The inside function here is going to be 5x, and its derivative, or something like it, is sitting around on the outside. So now what I want to do is I want to introduce something that you can do even when the exact derivative of u is not sitting around on the outside. As long as you have something close to the derivative of u on the outside, this method can still work. So let's let u equal 5x. Then du is equal to 5 dx. So we'll always have a du on the left side and a dx on the right side, and on the right side we should also have the derivative of whatever we started with in terms of x. So we'll get that. Now, let's say that we didn't have this 5 sitting out front, so ignore the 5 for now. Let's just say that we were integrating something like e to the 5x dx. What we're trying to do is we're trying to get rid of this dx and replace it with something that only depends on u. So to do that, what I could do is I could try getting this dx by itself in this equation. So in order to do that, what I could do is I could just divide both sides of that equation by 5. So I could divide both sides of the bottom by 5, and then I would get that du divided by 5 is equal to a dx. And the reason that's useful is because that allows me to take this dx in the original integral and replace it with a du over 5. So let's do that. So again, I'm trying to get rid of any expression that involves x. So I have a 5e to the 5x. 5x I should replace with a u. But I can also now replace this dx with a du over 5. So this would be a du over 5. And now here I'm multiplying by a 5 and dividing by a 5. So these will cancel. And this would just become the integral of e to the u du, which is e to the u plus c, based on our integral rules. And our last step, as usual, is just to replace u with its expression in terms of x. So we get the same answer that we got earlier. I just wanted to point out that you don't necessarily have to get exactly the derivative of u sitting around inside of your integral. It's okay to just solve for this dx term, like we did here, and then replace that dx with its corresponding expression in terms of u. So we'll see another example like that right away. So notice that in this case, I do have an inside function. It's a negative 3x. So we have an inside function, but its derivative is not sitting around on the outside. I don't have a factor of negative 3 sitting around on the outside. But let's try the strategy that we just used in e on this one, and we'll see if we can integrate still. So here, I know my inside function at least is a negative 3x. And what this would mean is that du is equal to negative 3 dx. And if you're ever unsure that you've written this second line correctly, you can divide both sides by dx and just check that you actually are getting the correct derivative of u with respect to x. So this is the same thing as saying that du dx is equal to negative 3, which is true. So that gives you sort of a way of verifying that you're doing that part correctly. But this is what we have so far. Now this is enough for me to write e to the u dx, because u is equal to this negative 3x. So that exponent I can replace with u, but this isn't good enough because we still need to get rid of this dx. We need to write it in terms of du. But thankfully I can take this bottom equation and I can solve for dx. I can get that dx by itself. That way we can replace the dx with something in terms of u. So if I take that bottom equation and divide by a negative 3, I would get du divided by negative 3 is equal to dx. And now that means that I can take the dx here and I can replace it with a du over negative 3. So this would become the integral of e to the u du over negative 3. And if you'd like, we can take that division by 3 outside of the integral because it is just a constant. So it's a multiplicative constant that we can factor out. And then we would get this integral. So that would give us a negative 1/3 e to the u after integrating plus a constant. And then for our final answer, remember all that we need to do is replace u with its original expression, which is a negative 3x, like that. So this would be our final answer for this problem. Okay, so this u substitution method will still work even if we don't get the exact derivative of u sitting around on the outside. We just need something sort of close to the derivative. So in this case, we didn't have a factor of negative 3, but that was good enough for our purposes because we could still just solve for dx and plug that into the integral. And then we were still able to reduce this integral to an integral only in terms of u. Okay. So let's look at this next problem. This one is again similar. So we have an inside function, and if you want, you can immediately try this technique. So you can pause the video and try problem G. I think you have enough information so far that you can do it, but it will be a little bit trickier than the previous problem. So here again we see an inside function, which is a negative 3x squared. The derivative of that, which is what we're looking for on the outside, would be a negative 6x. And we don't have a negative 6x on the outside, but we do have an x dx. So we don't have the -6 factor, but we do have something close to the derivative, which is at least the x part. And it turns out that this will be good enough for us to apply our u substitution. So let's just see what happens whenever we try it. So we'll let u equal the inside function. And that would mean that du is equal to -6x dx. So now we're going to plug that into the integral that we have up here. So we have the integral of x e to the -3x squared dx equals the integral of x. And it's okay to just start replacing individual pieces as you go. The important thing, though, is that you aren't able to integrate until you've gotten rid of all of the x expressions. So this would become an x e to the u dx. But you can't integrate this because here you have two variables going on. You have a u and an x. We need to continue simplifying this. But we can do the same thing that we did a second ago. I can solve this equation for dx to get an expression in terms of u. So maybe let's divide both sides of this equation here by -6x. So if I divide both sides by -6x, I would get a du divided by -6x is equal to dx. So I'm going to come back over to the integral and I will replace the dx with a du divided by -6x. And notice that now I have an x on the outside and an x in the denominator. So these can cancel. Oops. Sorry. These can cancel, and we would be left with just the integral of e to the u du over -6. And again, that division by -6, that's really just a multiplicative factor that's being applied to your integrand. So you can factor that out if you'd like as a -1/6 times the integral of e to the u du. And now we know how to integrate this. This will end up being a -1/6 e to the u plus c. And then for our final answer, we just need to replace u with its expression in terms of x up here. So we would end up getting a -1/6 e to the -3x squared plus c. And if you want to check your answer, you can just take the derivative of this thing that we just boxed, and you should get the original integrand. So that's how you apply u substitutions, even when u prime is not sitting around on the outside. You don't necessarily need u prime to be sitting around on the outside, you just need some multiple of it to be sitting around on the outside. In other words, you need something close to the integral of u to be on the outside. Sorry, the derivative of u to be on the outside. And then the u substitution will still work. So we'll continue doing a few more